Ya, eh, hello, talk about applications in biology. Now we're gonna explain some models. First, we're gonna explain a model about the spread of diseases, and then we're gonna analyze the predator-prey ecology. So, this chapter we do a quali qualitative analysis of the differential equations that affect this phenomenon. So first, I'm going to start introducing a concept that is called null climb. So this is a tool for analyzing nonlinear systems of differential equations. Especially we use it with planar systems because if we have a system in the form of the derivative of x1 equals f1 and so on till xn, the derivative of xn equals fn, that is a function of x1 till xn. This then nuclein is called the set of points where each xj the derivative of xj vanishes. So the xj nuclein is the set of points determined by setting the function fj to 0. Okay. And now this is the same. This is the same definition that I just explained. So that is the nuclein that is essential for for these kind of problems. So now we have the infectious diseases model. So this is called the SIR models, SIR model. So it's the acronym is because you have a susceptible population, then you have the infected population, and you have the recovered population. So we do a little bit of assumption. So first we say that the population is constant. The Since we're talking about populations, we assume S, I, and R are positive, and also they're a function of time. Uh, okay, so we also assume that the individuals who recover, they do not get sick again, like they gain immunity. So, okay, uh, we can next, please. Okay, so we also assume that the rate of transmission is proportional to the number of infected individuals and susceptible individuals, and these do like a relationship. If you multiply SI, like the susceptibles is related to the interaction between the infected and the susceptibles population. We also consider that the rate at which infected individuals recover is proportional to the number of infected. Then we see the derivative of R equals VI, where V is a positive constant. And okay, by one we get that uh, we can get the like how do you say like uh, we can obtain this equation here since we based on our assumptions we obtain the derivative of I. Okay, so we got the system. We have the differential equation system, and we also get S plus I plus R equals to a constant. Since that we if we get S and I, we can get R. So we'll simplify the system. Next, please. Yeah, but as we got one of those equations in base of the others, it's enough to consider this two-dimensional system. Okay, now we always do. Once we have the equation, we try to find the equilibrium solution. So we equal s to s, derivative of s to 0, and we get this. So replacing, we get that I is 0, and therefore this one is 0 too. So we get the equilibrium. It's I 0, and that means that we have the equilibrium on the x-axis. So next, please. So we linearize at 0. That is, we use the Jacobian matrix. We compute the Jacobian, and we evaluate it at s comma 0, and that's how we get this. And computing the eigenvalues are 0 and are bs minus uh, little b, I'm sorry, beta s minus b. So the behavior of the solution depends on the sign of this eigenvalue. Okay, we have that the solution is negative if s is less than v over beta, where beta is positive if we have that v over beta is less than s. That's what we get. Okay. Okay. We can also find the null claims to analyze the solutions. So for s, you take the derivative of s to 0, and we remember that s was beta multiply si. So we get the s is 0 or I is 0. Okay, so equaling this to 0, we get that I is minus v I derivative. Okay. And then for I, remember that we have to equal this I to 0. So there we get this equation. And then, okay, taking common factor I, we equal I to 0, and then we get S equals V over beta. So we get that the null claim is going to be for I. Can you go back? Yes, please. Yeah, so we get the null claim for I is going to be I0 and S equals V of I. We have here, we have S, we have I, we'll get I0 is going to be the S-axis, and S equals V over beta. It's going to be this one. Okay, next. So to analyze the nuclear behavior, we have to analyze by parts. So if we suppose, since I and S are always positive because we are talking about populations, we have that I is positive and S is greater than V over beta. We have that first VI is positive since V is positive and I is positive. So from this, we also get this because we get that beta multiplied by S is greater than V, and also we multiply by I, the whole expression, and we get this. So this is going to be positive. We also use this to get this one here. Beta Si is going to be greater than Vi. And it's also greater than 0 because we have this one here. So therefore, we'll get this also positive, and we'll get this one. So minus beta Si is going to be less than 0, and BSI minus VI is going to be greater than 0. So remember what we define in our system. We define that the derivative of I is going to be this expression, and the derivative of S is going to be this expression. We have that S prime is going to be less than 0, and I prime is going to be greater than 0. And that means that if we take, we go to the graph, like it's 2 pages. If we see this graph, how we analyze. So we have that in this section, S is greater than V over beta. So S is S prime is negative, so S is decreasing. But I prime is positive, so I is increasing. So the behavior is going to tell me that when I take values that are on the left of V over beta of S here, we take value here, it's going to tell me that I prime is going to be negative and S is going to be negative since the solutions come right here. And I prime is going to be negative because its I is decreasing. So that's what we see back there. But if you go back, we see this one. We have that I is greater than 0, and S, since S is have to be, it needs to be positive, is less than V over beta. We get this expression immediately, since S and I is positive and beta also is positive. From this we get this one too. Then we get this one, and we can get that S still decreasing. We also get that I prime is decreasing. So that's why I tell you when you are on the left side of S equals V beta. So okay, now we analyze the third equation. So we have when S equals 0, we have that this is 0. S prime, the derivative of S is going to be 0. So it keeps constant. But since this one is 0 and this one is greater than 0 and this is greater than 0, this is going to be negative. So I prime is going to be negative. So that's what happens. And so I is decreasing. That's what we see on the graph when S equals 0. Okay, now we can go to the next. So now we see when I equals 0. As such, if I equals 0, it's an equilibrium solution. Therefore, everything is constant. Okay, it's here. Okay, now we do another analysis. We have I prime, S prime. We divide it to get some function. So we need to analyze this rate of change. So we get to these ones, and then since I is function of time and S is also a function of time, we can get this expression, and we just replace, and we get this equation. From here, we can take integrals and solve, and we get to see this expression right here, that I equals minus s plus v over beta and log s plus c. Okay, now with this expression, we can see the phase portrait, and we can see the behavior of the solutions s over I, how they depend on each other. Okay, this is considered the phase portrait for the SIR system. Hey, next. Okay, now my classmate is gonna continue.
So for continue, we are going to consider a particular case of the infectious diseases. In contrast of the last case, we are going to take in mind the possibility of that S prime, is to say, if we talk about the susceptible individuals, we are going to plus an addition factor. Is to say, in this case, we consider infectious diseases where recovered individuals may lose their immunity and become reinfected with the disease. Okay, this is a case that consider the possibility of that. Once that you have recovered, you can be infected again. So we are going to assume that the return of the recovered individuals to the class S occurs at a rate proportional to the population of recovered individuals. Is to say, if we call R the number of recovered individuals, we are going to say that S prime, in addition to the last factor that was minus beta Si, we are going to plus the factor mu times R, where mu is a positive constant. We say us that this factor is going to be proportional to the recovered individuals. So this leads our Sears model like as we see. Is to say, S prime is going to be the factors that we were mentioned. I prime is going to be beta Si minus Bi, and R prime is going to be Bi minus mu R. And in comparison to the last case, we are going to see that if we sum S prime with R prime with I prime, this is going to be minus beta Si plus beta Si. Mu R minus mu R, and beta I and Bi minus Bi. So all these factors are going to cancel pairwise. So in summary, we are going to have that this sum is going to be 0. Or said in other words, we are going to have that S plus R plus I is going to be tau, where tau is a constant. And a positive constant, of course, because we are going to take in mind that both S, R, and I are positive numbers. And more than that, integer numbers, because all of that are numbers of individuals. And if we replace of one of these equations, is to say, if we take, for example, the last result, that S plus R plus I is tau, we're going to have that R is tau minus I minus S, is to say, this equation. So if we take this equation, we are going to reduce our system to only two equations: S prime minus beta Si plus mu times tau minus S minus I, and I prime equals to beta Si minus Bs, where beta, mu, and B and tau are all positive parameters. So we are going to continue analyzing how is the qualitative behavior of the system. For example, S prime implies that minus beta Si plus mu times tau minus S minus I is equal to 0. And if we consider the common factors S and mu, we are going to have that S times minus beta I minus mu plus mu times tau minus I are going to be 0. And this say us that while beta I plus mu is different to 0, we are going to have this result, mu times tau minus I over beta I plus mu. But if we resolve in another way, for example, if we factorize the I and the factor mu, we are going to have the I plus I times minus beta S minus mu plus mu times tau minus S is going to be equal to 0. So thus I gonna be mu times tau minus S over beta S plus mu. So for the same equation, we have two different results, one for S and the other for I. Which is the purpose of this? Well, the purpose is unique and is the analyze the null Klein's points, how we studied the last case. And now we're going to find the equilibrium points of I prime to S prime. I prime is equal to 0 only if beta Si minus Bi is equal to 0. We easily see that this implies that Bs minus beta times I is equal to 0. And this implies that beta S minus B is equal to 0 or I is equal to 0. In the first case, we easily check that S is going to be equal to B over beta. And in the second equation, I is going to be equal to 0. On the other hand, if S prime is equal to 0, we are going to have that minus beta Si plus mu times tau minus S minus I is going to be equal to 0. This is only for the definition of S prime, of course. So in this case, if we resolve for S, we are going to have that S is mu times tau minus I over beta I plus I. Of course, while beta I plus mu is different to 0. On the other hand, if we resolve for I, we are going to have that I is equal to mu times tau minus S over beta S plus mu. And we are going to take in mind, we are going to consider the results of the last equation. Is to say, for example, I prime is equal to 0 only if S is equal to B over beta or I is 0. And taking I equal to 0 and replacing that in the first equation for S, we are going to have that S is equal to mu times tau minus 0 over beta times 0 plus mu. And replacing S in the second equation, we are going to have that I is equal to mu times tau minus B over beta times B over beta plus mu. So for example, in the first equations, we have that B times 0 is going to be 0. And also in summary, we have mu times tau over mu, and this is equal to tau. In the second, we have that beta times B over beta are going to cancel the betas, and we have B plus mu. And in the numerator, the same expression. So our results are S equal to tau and I equals to mu times tau minus B over beta, all of that over B plus mu. So in this case, for this analysis, we conclude that we have two equilibrium points. The first one, tau, 0, and the second one, B over beta, mu times tau minus B over beta over B plus mu. So how we consider in the last chapters of this book, we can consider how is the qualitative behavior only checking the equilibrium points. Is to say, for example, if we know that these are the equilibrium points, and of course, the first equilibrium point is constant because we consider at the beginning of the case that tau is a constant, we are going to focus only in the second point. Is to say, what happens with the sign of T respect B over beta. And this is what we do in this page. So the first equilibrium point corresponds to no disease whatsoever in the population. Is to see that we see that I prime that that when I is equal to 0 is to say that we don't have infected individuals. And the second equilibrium point only exists when tau is greater or equal than b over beta. And when tau is equal to b over beta, the second equilibrium point becomes b over beta dot or comma mu times tau minus b over beta, and all of that over b plus mu. But replacing b over beta, we have that the first fraction b over beta, and the second mu times b over beta minus b over beta, and all of this over b plus mu. So this is only b over beta times comma 0. And what is this? If we check, we have that this is going to be equal to the first equilibrium points because we are considering that b over beta is equal to tau. So we have that these equilibrium points converge really in one and only one. See that tau over 0. So we can say that in particular case, the two equilibrium points coalesce to a tau comma 0. And the quantity b over beta is called the threshold level for the disease. And the linearized system is given by this expression. But how we get this linearized system? Well, we have to consider a function, a vectorial function, what we call a f, a big F, defined as this set plus t set times t set to R2, such that f as a vectorial function is equal to two component functions, which which each one is a scalar function. Is to say this function goes to R and this function goes to R again. And defining as our differential system is to say f1 equals to minus beta si plus mu times tau minus s minus I, and the second scalar function defining as beta si minus bs. So if we call y equals to s comma I, we have that df over dy is equal to the matrix given by the partial derivatives. Is to say the partial of the first f over s, the partial of the first f over I, and so on. And replacing, we have this df over dy is going to be minus beta I minus mu minus beta s minus mu beta I and beta s minus mu. So this is our general matrix that gives us the knowledge of how the linearized system will become, or which are going to be the qualitative behavior, no? So in the first equilibrium point, if we replace s as tau and I as 0, we are going to have this minus beta times 0 minus mu minus beta tau minus mu beta times 0 beta tau minus beta. This is equal to minus mu minus beta tau minus mu 0 beta tau and minus b. So the eigenvalues we can obtain in an easy way because this is a triangular matrix. And what are the eigenvalues? We see that directly are minus mu and beta tau minus b. And for tau greater than b over beta, we have that b tau minus b is greater than beta times b over beta minus b. Only taking this equation, multiplying by beta and subtracting minus b, subtracting b. And solving this, we have that the beta are going to cancel, and we obtain b minus b, that is 0. So we have the b tau minus beta tau minus b is greater than 0. So when tau is greater than b over beta, tau comma 0 is a saddle point. Why a saddle point? Because we have that this eigenvalue is positive, but minus mu is a negative eigenvalue. So we conclude that this is a saddle point, and on the contrary, an unstable source. Well, so when tau is greater than b over beta, the point tau comma 0 is a saddle, and if tau is less or equal than b over beta, an unstable source. And the second eigenvalue, if we consider the second eigenvalue, we have this matrix. And if we solve for each component, we have, for example, in the one, minus beta mu tau plus mu b minus mu b minus mu squared over b plus mu, minus in the second component, the betas are going to cancel, and we have minus b minus mu. In the third component, we have that entering the beta in the fraction, we have beta mu tau minus mu b over bo plus mu. And in the last component, where we easily check that this is 0. So we have that this matrix is equivalent to minus mu times b tau plus mu over b plus mu minus b minus mu times b minus beta tau over minus b minus mu, and 0. And we observe immediately that the determinant of this matrix is only the product of the contrary diagonal with the opposite sign. Is to say, we have, for example, that if we multiply this factor with this, the denominator are going to cancel, or is going to cancel, and we have only that mu times b tau minus b is the determinant of A. And the trace A is minus mu times b tau plus mu over b plus mu. And we see that this factor is positive and the second one is negative, of course. But of course, this factor is positive if and only if beta tau minus b is positive. So we are considering to the right side of our point tau equals to b over beta. And for this result, we can take in mind the chapter 4 of this book, which say us that both eigenvalues have negative real part. And so this equilibrium point is asymptotically stable. Biologically, this means that the disease may become established in the community only when the total population exceeds the threshold level. The threshold level is the point that we at the beginning called as tau equals to b over beta. And we will only consider this case in what follows. Know that the SIRS system is only of interest in the region given by I, S greater or equal than 0, because we are considering the number of individuals, of course, and S plus I minus than tau. Denote this triangular region by 1, of course. Know that the I-axis is no longer invariant while while the x-axis solution increase out to the equilibrium at tau times 0. But for this, well, we are going to see this better in our next page. So for next, we have that the region, this region is possibly invariant. For see that, we have to check that the direction of the vector along the boundary of the region is tangent to the boundary along the lower edge I equals to 0, as well as at 0 times tau. Along S equals to 0, we have that S prime is equal to mu times tau minus I, and this is greater than 0. So the vector field points inward for I between 0 and tau, because it's only in this case that this second factor is positive, of course. Along the hypotenuse, if S is between 0 and b over beta, we have that S prime is minus beta Si, which is negative. And I prime is equals to I times bs minus beta, which is less or equal than 0. So the vector field points inward. And while S is between b over beta and tau, we have that minus 1 is less than I prime over S prime, which is equal to minus 1 plus b over beta S, which is less or equal than 0. So again, the vector field points inward, and this completes the proof. On the other hand, we already see that the I-null lines are given as in the SIR model by I equals to 0 and S equals to b over beta. And the S-null line is given by the graph of the function. So if we consider in addition the study of two derivatives, well, the S-null line, we already see that has this form, mu times tau minus S over bs plus mu. And doing Strike-Worth calculations, we are going to have that I prime S is less than 0, and the second derivative of I spec S is positive. So this null line is the graph of decreasing and concavity functions that passes through both tau, comma 0 and 0 tau, as we show in the figure, this figure. So we see that how is the behavior, of course. We can say that this is an asymptotic equilibrium. In this phase portraits, all solutions appear to tend the equilibrium point S prime, I prime, and the proportion of affecting susceptible individuals tend to a steady state.
Okay, now we analyze a predator-prey system. We consider a pair of species, one of which consists of predators with a population that is denoted by Y, and the other it's prey with population X. We do some assumptions first. The prey population is the total food supply for the predators. Yeah. So the predators gonna eat only the prey. In the absence of predators, the prey population grows at a rate proportional to the current populations, such as what we saw in the first chapter. So we have a constant growth of population depending on the present population. Okay, so we have, if we don't have no predators, Y is 0, and we have X prime equals AX with A0, okay? So when predators, another assumption, when predators are present, we assume that the prey population decreases at a rate proportional to the number of predator-prey encounters. So we have that's how we get that v times x xy, because we have the xy is the encounter with the predator-prey, and we have the proportional decrease. That's why we get the minus. So in the absence of prey, the predator population declines at a rate proportional to the current population. So we have the same assumption as chapter 1 of the book. So we get when we have the x equals 0, we have the y prime equals minus cy with c positive. And also we know the solution. That is y is equal to the initial solution y0, y sub 0, taking the exponential at a times t. When there are prey in the environment, we assume that the predator population increases at a rate to the predator-prey method. So of course, if we have prey, the predator population is gonna eat them, and the population is gonna increase. But it's gonna be proportional on how they meet. So that's how we get our predator prey system. This is also called the alternate local system. So we have x prime, this expression like equals a times x minus v xy. We also have y prime minus c times y plus d times xy, where a, b, and c, d are positive. So we also, since we're dealing with populations, we assume x and y are positive or negative. As usual, our first job is to locate the equilibrium points. So this occurs when x and y equals c over d and a over b. We also compute the linearized system with the Jacobian matrix, and we get this matrix. And we can also get the x nuclei. So, but first with the Jacobian matrix, if we analyze when x and y equals 0, we get eigenvalues equals a and c and minus c. Sorry. So in this equilibrium point, x equals 0 and y equals 0, we get that we got a positive, negative eigenvalues. Therefore, we got a saddle. We have a saddle, and that means that we have a stable and unstable curves. Then, if we use this equilibrium point, we replace it here, we're gonna get imaginary eigenvalues. Okay, but we cannot conclude yet. Okay, so we sketch the nuclei for this system, and we using what we did before. So the x nuclei is gonna be when x equals 0 and when y equals a over b. So we have here in this graph, here and here, and we also have the y nuclei when y equals 0 and x equals c over d. That is what we explained before. So we only consider the region where x and y is positive, and we divide this quadrant of the plane in four regions. Okay, now we do the same analysis that we did before, and we'll get that the solutions are running counterclockwise about the equilibrium point. So next, so what we do now, we have we need to employ a trick to separate these two variables. And for that, we use what is called a Lyapunov function. And okay, if we use the Lyapunov function, we suppose this. So we take derivative with respect to time, and using the chain rule, we get this. Now we replace the values that we had in our model, and we get this expression. Okay, with with that expression, we simplify, um, we obtain equaling the derivative to L to 0. This this accomplishes when we get this expression. So we get that this expression is gonna be possible only when L prime equals 0. That means the expression only is possible when this right here is a constant. Okay. Here next. So what we do is we set this constant equal to 1, and therefore we can do this simplification of the variables with the equations that we just have. So we pass it to the other side and simplify. Now we have two equations. If we integrate, we find these two other equations. Now we combine them, in our function. We combine them to this. And if we take the partial derivatives of this function, we can see that when we we compute this c, like it's gonna be our minimum for the Leibniz function. Thus, as we have what we saw in the chapter, we get that c is gonna be a stable equilibrium for the system. Um, that's gonna be all for now. I don't know if Jan has anything to say right now. Then that would be all. Thank you.